Hello everyone, welcome to my channel. Today we are talking about stiffness matrix using unit displacement method. So first of all, let's go with the definition. So the stiffness matrix is a matrix of forces required to produce unit displacement at each degree of freedom, while all other degree of freedoms are held fixed. Which simply means that we know F equals to KU, where F is the force, K is the stiffness of the member, and U is the displacement, right? So here we're going to find the stiffness of the member using unit displacement method. What that means is, for example, if you say U equals to 1, then you get F equals to K times 1. Then what happens is the stiffness turns out to be the force. From this definition, what you can understand is that if you put unit displacement at each degree of freedom and calculate the forces, keeping other degrees of freedom fixed, that is, zero displacement at other degrees of freedom and unit displacement at the particular degree of freedom, then the force resulting forces will form the stiffness matrices columns. So, for example, let's say we have a member like this. We have two members. This is member 1. This is member 2. Here, as you know, we have 6 degrees of freedoms like this. Right now, I'm just roughly saying it. We are going to do the full derivation of this. So, for example, this is U1, this is U2, this is U3, this is U4, this is U5, and this is U6. For example, you say, okay, let's keep U1 displacement at 1 and U2, U3, U4, U5, U6 as 0. Then resulting force will be equivalent to first column of our stiffness matrix. Okay, and if you keep U2 as 1, and all of this as 0, then you will get the second column. With U3 you will get the third column, with U4 you get the fourth, fifth, and then sixth, and so on. Okay, so we are going to keep unit displacement at U1 and we are going to get the first column. Then we are going to put in U2 and consecutively until U6, and we get all 6 columns, and then we get our stiffness matrix. So in the right of the screen you can see I have created this stiffness relationship for our truss element. So you know this F equals to KU. So for example, if you put unit displacement at U1 and all other as zeros, then you are going to get the first column of the stiffness matrix. So if you keep U1 equals to 1 and find the forces, you are going to get this column. Okay, if you are going to put let's say U2 equals to 1 and other zeros, then you're going to get this column and so on. So if you put here U2 equal to 1, you're going to get this. If you're going to put U1 equal to 1, you're going to get this, and u3 equals to 1, u4 equals to 1, you're going to get all of this. And you will get this whole matrix. So we are going to solve this cross problem totally, and we're going to find out how we can find the stiffness matrix using the unit displacement method. So let's go. So here is the problem, and let's go stepwise. So let's start with the step number 1. So in the first step, you need to simplify the model. Okay, simplify the model, and you're going to have one more thing here, which is the normal force, which is this member internal force here, which is going to be like this. You're going to have this convention fixed on your head. Follow only one convention. So I'm going to put this compressive convention in all the cases. Okay, just stick to this. So now step number 2 is put displacement u1, that is here, equals to 1 and others 0, others fixed. Okay, so if you do that, what you're going to have is your figure is going to look something like this. Move. So when you move this node 1, you're going to move it along this path to right here, and this is going to be the unit displacement 1 that I was talking about since the beginning. And then we're going to have this member quite like this. So this is initial case before we apply the unit displacement, and this is final after we apply the unit displacement at node 1 as shown in the figure. Now just you need to do some geometry here. We need to find what you need to find here. Find the change in length. Find the change in length del L. Since we moved this node to the right, this member is going to be compressed because the length in the final position is going to be shorter than in the initial case. So this member here is going to be compressed, right? It's going to be compressed because the length is decreasing. So if you construct a little line perpendicular here, quite like this, and you already know this angle is phi, then what you can do is you put cos of phi here in the triangle I just constructed over here. Then cos phi is going to be minus del L divided by 1 is the unit length. So therefore change in length is going to be minus of cos 45, as pi is 45, and del L is going to be minus 1 over root 2. And why did I keep minus here? Because it is compressed. The length is reduced. If the length was increased, elongated, I would have put positive sign here. Okay. Since you already got this change in length here, now we are going to calculate the internal force. Okay, internal force, which we say N. So in this case, N1 equals to K1 times change in length del L. So N1 is the internal force. For case 1, K1 is the stiffness of the member 1. As we already drew in this picture, that the stiffness of this element here is K1 and this element is K2, and since we moved this element K1, we are going to have K1 as the stiffness of that member, right? So here we used N1 equals to K del L, which is similar to F equals to KU. The difference is only that here for F we keep N, and for U displacement we keep change in length del L. Okay, so from here you can get N1 equals to, and the value of del L is minus 1 by root 2, so you get minus of K1 by root 2. So this is your N1, and you are going to use this for balancing the equilibrium. Okay, I'm just going to do this here in the right section. So using equilibrium law, using equilibrium law of forces, what we can get is that for the first case I'm going to be explaining in detail, and after you get this I'm going to speed up this tutorial. So this is F1, F2, and this is F3, F4, F5, and this is F6. But remember, we also said that we have this internal force here, which is going to be in equilibrium with the external forces, right? So we're going to use this. And for this case, what is our member that we are talking about? That unit displacement at U1 is going to have its effect on this member, right? On this member. So we are going to have the equilibrium, force equilibrium here. Okay, you apply force equilibrium in this member. So if you apply force equilibrium in that member, then what you will get, summation of Fx equals to 0, then what you get F of 1 plus n of cos phi equals to 0. How you get that? It is very simple. You get this because, let's see, in this member, this is F1, this is F2, right? And this is your n. So if you construct this a little bit here, and you have this angle as phi, then if you use n cos of phi, then this is going to be n cos phi. So this is going to be n cos phi. So this equilibrium is going to be like this. All right. So from here, you are going to get F1 equals to minus n cos phi. So F1 equals to minus, so value of n is here minus k1 by root 2. So you just put minus k1 over root 2 into cos phi is 1 over root 2. Therefore, you get F1 equals to k1 over 2. First element we got here. Now we do summation of Fy equal to 0. This is also for node 1. Okay. If you do that, then you're going to get F2 minus n sine phi equals to 0. Then F2 is going to be positive n sine phi, since value of n is minus k1 over root 2, sine phi is 1 over root 2. you are going to get minus k1 by 2. Therefore, f2 equals to minus k1 over 2. This is our second element. Now for node 2, that is for this node, we are going to do the same thing. If you do summation of fx equals to 0, then what you are going to get is f3 minus n cos phi equals to 0, and f3 is going to be positive n cos phi. So minus k1 over root 2 into 1 over root 2. So f3 is going to be minus k1 by 2. So if you do summation fy equal to 0 in node 2, then what you are going to get is f4 plus n sine of phi equals to 0, because both of them are in positive direction. f4 equals to minus n sine phi, and f4 is going to be, what is our value of n? It's minus k1 over root 2, so minus k1 over root 2 times 1 over root 2. Hence you get f4 equals to k1 over 2. So if you are wondering how we come up with these equations, then I'm just going to show you an example with node 1, let's say. And if we put the equilibrium along x direction at node 1, if we do summation fx equals to 0, then as you can see, f1 is in this positive direction, and n cos phi is also in this direction. So it's going to be f1 plus n cos of phi equals to 0. Okay. And if you say f2 is in this positive direction, whereas n sine phi is in this negative direction. So for fy, what you are going to get is f2 minus n sine phi is going to be 0. So if you look at node 2, f3 is in this positive direction, whereas n cos phi is in this direction. So it's going to be f3. This is for node 2. f3 minus n cos phi is going to be 0. And if you look at f4, this is in positive direction, and n sine phi, this is also in positive direction. So f4 plus n sine phi is going to be 0, just in case if you are wondering. So now we are just going to assemble all these elements, the forces, to get the stiffness matrix. You just need to understand one more thing, that f5 and f6 is going to be 0 for u1 equals to 1. So if you look at this figure, if you put f1, if you put unit displacement along f1 direction, then it is not going to impact on f5 and f6. So the values are going to be 0 here. So your first column is going to be first column is going to be f1, f2, f3, f4, f5, and f6. If you plug in all the values that you found out, then see f1 is k1 over 2, f2 is minus k1 over 2, f3 is also minus k1 over 2, f4 is positive k1 over 2, f5 is 0, and f6 is 0. So this is your first column. Okay. Now let's go to step number 3. Now we put u2 equals to 1. What does it mean? It just means that we have this structure. This was our u1, and now we are going to put u2 unit. That means we are going to shift this node to here using u2 equals to 1. So this displacement is 1. So now our member is going to be something like this, right? Sorry for the drawing, but I hope you understand this. So it's going to be like this. Now you can clearly see that this member is elongated. This member is elongated. So change in length will be positive, not negative. Okay, it's going to be positive. So here also you do a little geometry here. So you know this is phi, this angle is phi. And now if you draw perpendicular to this section, then you are going to find that del L, which is the increase in length. This is our del L. Okay, this is our del L. And this little guy here, this thing is our phi now. Okay, this is our phi. This is 90 degree. This phi is, this angle is phi, and this is 90 degree. Okay, just perpendicular. Now here, so if you do sine phi in that little triangle there, then you get del L over 1. And I put positive here because it is in tension, it is elongated. So del L is going to be sine 45. Therefore, del L is going to be 1 over root 2. Similarly, we use n equals to k times del L. Then we are going to get n equals to k1. Why k1? Because we are still in this first member. This is k1, this is k2. Del L is going to be 1 over root 2. Therefore, we got n equals to k1 over root 2. Now we are going to repeat the similar process of equilibrium. So if you do the first case, you're going to get f1 equals to minus n cos phi is going to be f1 equals to, it's the same thing, but just the value will be different here because n1 we're going to put k1 over root 2. So k1 over root 2 into 1 over root 2, f1 is going to be minus k1 by 2. Okay, similarly, if you do this, f2 is going to be k1 over 2, f3 is going to be k1 over 2, f4 is going to be minus k1 over 2, and f5 and f6 is going to be not affected. That's why they are going to be 0. Okay, so now you finally get the second column. Okay, so second column is going to be f1, f2, f3, f4, f5, f6 transpose. This was our step number 2. Now in step number 3, what you are going to do is you are just going to put this displacement as unit. So this node is going to be transferred to here, unit distance. So this is u1, this is u2, so then this is u3. So u3 equals to 1 is going to move the member to this direction. So we're going to have construction like this. Okay, let's use the different color for the deformed structure. So after being deformed, it's going to be like this here, and this member is going to be like this. So now this displacement is going to affect both elements. So this member, you can easily see that this member is elongated. Del L is positive. This member is compressed, so it's negative. Okay, it's negative, and you just follow the same convention for n here and here as well. Let's zoom a little bit for this section only, because this is very important to learn. So this element is actually changed to this configuration, right? So then what is the change in length going to be? The change in length is going to be this term here. This E is our change in length now. This E is our del L, which is going to be positive. Okay, it's going to be positive. So what you can get here is, if you use cos phi in this triangle, then it's going to be del L over 1. And why is this positive? Because it's elongated. Positive. So del L is going to be positive 1 over root 2, right? And if you do the equilibrium similarly, like for F1, for node 1 and node 2, F1, F2, this is going to be F3, this is going to be F4, and we have another section here, F5 and F6, and this time these two elements are not going to be 0. Okay, so this change in length del L is for, this is for the first element, okay. So for the second element, what is it going to be? So in case of the second element, originally you had configuration like this, but then you pushed the node from here to here, right? And finally the configuration changed, and the configuration reached here, right? Like this. Okay, just consider this as a straight. Now what is the change in length here? Change in length is simply like this. It's going to be 90 degrees, and this is going to be change in length, which is going to be negative. Why? Because the member is compressed, so it has to shorten, right? It has to shorten. So for this element, if you use cos phi, then you're going to have del L over 1, because this is 1 and this is phi, Okay, then what is going to be del L for the case 2? Let's say this is del L1. For L2, it's going to be 1 over root 2. But it is negative, right? Don't forget that. I didn't get confused. I was just checking. Okay. So we got the del L's. So for element 1, stiffness is K1, okay? Just don't forget that. So similarly, we are going to put the formula that n is going to be Ku, right? But here we are going to put K del L. So just for remembering, okay? So n is going to be K1, and change in length del L for member 1 is positive 1 over root 2, positive 1 over root 2. Therefore, n for this case is going to be K1 over root 2, and this is what we are going to use when we are going to use the equilibrium equations. And similarly, if you do the equilibrium equations, like I said earlier, then you're going to get F1 equals to minus n cos phi, and you're going to have minus k1 by 2. Therefore, F1 is going to be minus k1 over 2. Okay. Similarly, you're going to have F2 equals to k1 by 2. You can do this. I just skipped the process because it is similar. So F3 is going to be positive k1 by 2. Okay. And F4 is going to be minus k1 over 2. We are only looking for the equilibrium for this case and this case, where we are using stiffness k1 for this element. Now, if we look at this element, we are again going to have the impact in here F3 and F4, and then we're going to add. And here you have to remember one thing, that due to the unit displacement at U3, for the element 1, we are talking about F5 is not going to be hindered and F6 is not going to be hindered. So F5 and F6 is going to be 0 for this case. Okay. So let's go and look for element 2. Okay. So for element 2, when we say element 2, we mean this, and this is F3, this is F4, this is F5, and this is F6, right? So this is the final configuration that we have. And initially it was over here, and we just shifted this to this location. So I just point out this initial location here. The white is the initial position, and consider this is straight. Okay, so this is the initial and this is the final one. So you can easily see that this is compressed and del L is negative, and that we found out to be del L2 is minus 1 over 2, right? And then now change in length, you are going to find, if you little bit make perpendicular here, and this is our phi, then this is del L2. Okay, so you just put the equilibrium. We already did it here. Okay, so just put the equilibrium for the second element, then you get F1 as 0, because for the second element, this F1 and F2 is going to be unbothered. Okay, and F2 is also going to be 0 for this case, but F3 is going to have something. So if you look at F3, and we have this n, see n and F3, and if you do equilibrium in along this x direction, then you get F3 plus n cos phi equals to 0. Okay, and the value of n, what is the value of n here? So for n equals to k times del L, n equals to k is k2 for second element, and del L is minus 1 over root 2, which is this del L2. Therefore, you get n equals to minus k2 over root 2 k. Hence, you get F3 equals to k2 by 2 positive. Okay, and then so F4, basically this is F4 and it's going up, so it's going to be positive, plus n of sine phi is going to be 0. In case you are just wondering how this equation came, then I would just like to show you. So this was our condition, right? So this is F3, this is F4, this is our n, right? And this was our phi because we had our structure like this, and this was phi, so this is also phi. So this element is going to have n sine phi, and this is going to have n cos phi. I hope it is clear. So f4 is going to be minus n sine phi, and minus n sine phi is going to make it, so it's going to have minus of sine phi, right? And n is going to be minus, so it's going to be positive. Okay. Now for f5 and f6 also we do the similar thing. I shouldn't have erased that thing earlier. Anyways, so this is our f5 and this is our f6, and we have our convention set so that we do not get confused. This was our phi. So if you use equilibrium in this case, what you are going to get is f5 minus of n cos phi equals to 0, because n cos phi is going to be this direction, which is negative. So f5 is going to be positive n cos phi. Since our n is minus k2 by 2, it is going to be minus k2 over 2. And if you look in this f6 direction, it's going to be f6, but this n component is going to be in this direction, and it's going to be n sine phi, but we have to do it in negative way because it is the negative direction. So f6 is going to be positive n sine phi, and if it is positive n sine phi, we are going to have minus k2 by 2 as f6, right? So let's just accumulate all those things which we have so that we can finalize our column number. Which column number is this? This is column number 3rd. So third column stiffness is going to be f1, f2, f3, f4, f5, and f6, right? But see, for the first element, for element 1, this is for element 1 over here. We got f1 minus q1 by 2. We got minus q1 by 2, but for the second element, for element 2, we have f1 0 and f2 0. So we have to add f1 plus f2. But since for the second element it's 0, so we are just going to have minus k1 over 2 here. And for f2 also, we are just going to have this element here, k1 over 2. Okay, this thing is here, this thing is here. And now for f3, we have this value for the first element, but for the second element, we have this. We just need to add both of it. So for the first element, we have k1 over 2. For the second element, we have k2 over 2. For the fourth element, we have minus k1 by 2 here. And for this, we have positive k2 over 2 plus k2 over 2. For the fifth element, we have 0 here. For the sixth also, so 0, but here f5 we have minus k2 by 2. Just put minus k2 by 2. And for f6, we have 0 here, but here we have minus k2 by 2. Just put minus k2 over 2, and this is your third column. So we have our first column, we have our second column, and we have our third column. Now for the fourth column, so for fourth column, you just put u4 equal to 1. What does that mean? That means This is our original configuration, right? But now you just put, so this is U1, this is U2, this was our U3, but now U4 means you just put this node and then you just shift by unity, by 1 here. This is 1, 1, by 1 distance, just shift it here. So your new configuration is going to look like this. Here and here like this. Okay, so both of it is going to be compressed. This is also going to be compressed. Then del L is going to be negative. This is also going to be compressed. Del L2 is also going to be negative, right? And just draw the perpendicular line here so that you just be clear how you derive this. Okay, this is 90 degree, this is 90 degree, and this, since this angle was our phi, right, this would be our phi here and this would be our phi here. So using this you just do the geometry when you resolve those things. Okay, so if you do this fourth column, then you're going to have your stiffness matrix like this. So fourth column is going to be, I just skip those part. Okay, it's the same thing, just didn't want to repeat it. So you are going to have, just so that you can check the answers, this is minus k1 by 2. Here you are going to have minus k1 by 2 plus k2 over 2. Here you are going to have k1 over 2 plus k2 over 2. Then you are going to have minus k2 over 2 and then minus k2 over 2 again. Transpose just to separate this. This is the first element, second and third, fourth and fifth and sixth. Okay, so for fifth column, you just make sure that when you resolve the thing, just put the direction for the n like this. Okay, otherwise you are going to mess around. So just put the direction like this and everything is going to be fine during the equilibrium. So for the fifth column, it's now really simple because this is our original configuration. And so for the fifth column, you just need to put u5 equals to 1, and this is our u5. So you are just going to shift this by unit distance. So this is going to be your new length. This is elongated, so del L will be positive. Change in length is going to be like this, and this length is going to be del L, right? And this is going to be phi, of course. This is going to be phi, and just put direction of normal force like this. Solve the equilibrium, then you'll get fifth column as, so you're going to get fifth column as 0 0, which is understandable because shifting this is not going to affect in this direction. Minus k2 over 2, minus k2 over 2, k2 over 2, k2 over 2. Okay, fifth column is set, and the last column is going to be for sixth column. What I'm going to have is, I'll just draw the picture. So you add this as original. So this is going to be unit length 1. So you can clearly see this is elongated, so change in length is going to be positive, and the change in length value is going to be this one. The arrow is a little bit mistaken here. This one, this from here to here, it's going to be del L. Okay, and you just put the equilibrium conditions, and when you solve it, you are going to get sixth column as like this. Again, 0, 0 minus k2 over 2 minus k2 over 2 k2 over 2 and again k2 over 2. Okay, so final step is assembling all the values. When you assemble all the values, you are going to get your stiffness matrix like this. If you have any questions, just put in the comment section. Thank you guys.